Welcome back, everyone. So let's have a look at this problem here, just to sort of start things off. So we have a circular bicycle path. AD is a diameter, and we're also told that BC is perpendicular to AD. Okay, so I'm going to mark that in the picture here. So if BC is equal to 6x and BAC is x plus 22, compute BC. All right, I think that seems pretty fair. Notice that BAC here, right, we can see that if I were to draw this portion here, let's go ahead and do that. Notice that BAC here fits the definition of an inscribed angle here. And we know that the inscribed angle, right, is 1/2 the intercepted arc. So that tells us here that the measure of angle BAC here, or x plus 22, is going to be 1/2 of the arc it cuts off, which is 6x. So we can kind of put this together. This gets out very nicely. So you get x plus 22 equals 3x here. So you get, I think, 2x equals 22. So x is 11, right? Okay. So it makes sense, therefore, that this is going to be 66 degrees because it's going to be 6 times 11. So we get 66 here, and therefore BAC is 33. And that seems to work out very nicely. Cool. Now, BC has a length of 2. If Seth at B is meeting me and at E, how far does he have to walk if we walk along this here? Now, our instinct, we look at the problem here, when we assume the diagram's drawn to scale. Our instinct tells us that BE should be 1/2 of BC, right? So that means it should be 1. But of course, that's just an instinct. That's not exactly, does it have to be true? Well, let's take a look. Maybe we can figure something out here. Well, there's the center of the circle. And again, usually when you're dealing with circle problems here, it's often a good idea to just draw in some radii. So I'm going to draw in the radii here, OB and OC. Now we know that the radii here are congruent, so that means these are congruent here, so I can mark that. We know BC is perpendicular to AD, so I got some right angles here. And notice that it's pretty clear OE is congruent to itself. So now, if we look at problem number 2 here, right, considering what's going on, it looks like I have two congruent triangles, right, OBE and OCE here, right? These two triangles appear to be congruent, and it looks like it's, again, hypotenuse-like here, yep, right? So as a result, we know that these two pieces are congruent here, and we know therefore, so that means this implies here that BE is congruent to EC here, right? And therefore we know that this has to be 1. Now, another thing to note here, wait a minute, that's not the only congruent bits here, right? We also know there are other congruent bits. In particular, these angles here, right? We also know that one other consequence of this is the fact that angle BOE and COE are congruent, right? Right, so we know that's the case here. That's the situation. But wait a minute, if you look at the picture again, we see that O is the center of the circle. BOE and COE are both central angles. And remember that central angles give their measures to the arcs they cut off. So that means in this situation here, this means that BD and CD, the arcs are congruent here as well, right? So therefore, we now know, notice that this line here, this diameter, it splits this, if it's perpendicular to this chord, it actually splits two things. It splits the chord in half. It also splits the arcs in half as well. So that actually tells us something very important here. So we get this particular thing here. We know, the result, I actually just proved this here, that if a diameter is perpendicular to a chord, then it bisects that chord and the arcs of that chord as well. So not only does it split the chord exactly in half, but also splits the arc at the end in half as well. So that gives us an important thing that we can take a look at here. And also note here, one other important note is that the perpendicular bisector of any chord passes through the center of the circle. We actually use this sort of intuitively when we were looking at the circumcircles of triangles with constructions, right? We kind of did this sort of thing in the past, okay? Now, another particular theorem I want to focus on here, now you have that. Another particular theorem I want to focus on here is this, that if two chords are congruent here, then the arcs they cut off are congruent. Now, actually, this proof is not that hard to show. So I'm going to go ahead and do this one really quickly so we can kind of see why this is the case here. All right, let me go grab my pen. Notice here, so we have two congruent chords. So we're saying that if AB is congruent to CD here, right, that is going to imply that AB, the arc, is congruent to CD, the arc, right? So this here, we want to show this. Okay, so we want to show that this is the case here. Luckily, this is not that hard of a proof, right? Because if you think about it, well, with the circle, we need its center. Okay, it seems like congruent triangles are going to be the bit here. So let's draw in some lines. Yet again, drawing in the radii really helps here. So we're going to draw radii AO, BO, CO, and DO, right? And notice that these are all congruent to one another here. So this allows us to conclude that triangle AOB is congruent to triangle COD by side, right? We have side here, luckily. And this, well, let's see, that tells us these angles here are congruent, right? That tells us that angle AOB is congruent to angle COD here, and those are central angles, which leads us to our goal. So notice that actually works out very nicely here. We end up with something that looks like this. But wait, there's more. Because if you think about it here, this proof seems to be, this seems to work out very nicely here. Can I go backwards? If I start off with AB being congruent to CD here, if I start off with that being the case, can I show that the chords are congruent? Well, again, we can do the same thing here. Yet again, I can draw the radii. AO, BO, CO, and DO here, right? I'm going to go ahead and sketch this down here so we can see it a little bit more, right? So we can draw the radii in here, right? Here. Right? So now, here's AB, here's CD here. Now we're going to start off with these being congruent. Now I want to get to these being congruent. So yet again, we can do the same thing by drawing an O, the center of the circle, like this here, and connecting our radii, like so. Right? So here's a radius here. Here's a radius. We know these are all congruent to one another. That's going to be important to us, right? Now, note that in this situation here, because these angle arcs are congruent here, we know that the arc measures are given to them by the central angle. So the central angles are congruent here as well, right? And then here we can conclude from this that angle AOB is congruent to angle COD here, right? So that's our case here because these are central angles. And now we have the fact that triangle AOB is congruent to triangle COD by SAS here. And as a result, we get the fact that the two chords are congruent. So notice that the theorem actually works in both directions here. You can actually go if and only if. It's a biconditional statement here that'll work out very nicely. And note that these theorems here all work out very nicely. And we've actually taken a look at several of the other theorems before. We actually looked at them yesterday here, right? So this particular one here, right? The two inscribed angles intercept the same or congruent arcs are congruent. We talked about that yesterday, so I just want to review that here. If you're not sure about this, refer to the proof from yesterday here, or the previous lesson. And then also here, note that if two chords are parallel, they cut off congruent arcs between them. And that's also part of the homework as well. Now note that this works out very nicely, so you should be okay with this here, and you end up with something that looks like that.